Okay, so we're going to talk about climate change next, which makes a lot of sense because it's colder and frickin' here. Does anybody else think that? Man. Alrighty, so climate change and integrating that into landscape planning. We've talked about that a couple of times today. We have Emily Henderson and Jessica Halofsky here to talk to us about that. They're both with the Institute for Natural Resources at Oregon State University and/or University of Washington. And help me welcome them while I pull up their presentation here. And you are... Where?
Just right your cursor. Yeah. Up, down, yeah.
Up, down, there?
Up.
Up. That one?
See that? Yeah. Great.
Okay, there we go.
Alrighty. Thanks, Cheryl. And thank you for sticking it out for this long. I know it's starting to get cold in here. I keep hoping it's going to warm up. So we are going to, Jess and I, she's still sitting down there, she'll pop up in a minute to fill you in on a lot of the most exciting results in here. I'm going to talk a little bit about sort of a landscape modeling framework that can be adapted to better account for climate change. So I'm actually going to spend a fair bit of time on the non-climate change aspects of it and point out to you where it falls short, where we could do things better, and Jess will then fill you in on how we can do things better and how she's already doing things better and we plan to do things better. So, a little bit of philosophy. I think a lot of people, anybody here who has done any modeling will has probably heard this quote in some form or another. Essentially, all models are wrong, but some are useful, and I think all of us who do this hope that we are in the latter category of being useful rather than just plain wrong. And all of us have probably encountered skeptics who will look at our work and say, bah, it's only a model, of course it's wrong. So this is kind of how I tend to look at modeling processes. They are frequently kind of complicated. They are hopefully useful. It's our best estimate of codifying our assumptions. That said, they do fall short in many ways, and understanding those can help you glean what is useful out of a model that is wrong. So, there are a couple of projects which are really behind today's talks. Some of you may have heard of the Integrated Landscape Assessment Project. I know there were some familiar faces in here who were involved with the ILAP predecessor, IMAP. That was a multifaceted project which grew out of the Forest Service originally and then ballooned with the American Recovery and Reinvestment Act. And it had a couple of modules which were oriented primarily towards talking about what might happen in the context of climate change. And one dimension of that study did some work which was focused in Central Oregon. Like I said, you'll hear a little bit more from Jess on that in a minute. And there was also an offshoot project which the Northwest Climate Science Center funded just this last year, climate management and wildlife habitat in the Pacific Northwest. So that CMH project is what I'm going to be talking about a little bit more, which, as Caroline mentioned, her project is still in the early phases in the development phases. The same is true with the CMH project. So you'll hear a little bit about where we're planning on going, and then Jess will fill you in on some of the details about how we're going to get there. So it's a project looking at basically three focal areas: coastal Washington, southwestern Oregon, and southeastern Oregon, and we're curious to know how climate and management might interact to shape what the world's going to look like in the future, and specifically in the future what it might look like with respect to some wildlife habitat. So we're looking at a matrix essentially of 9 different possibilities to look at. It's an intersection of hypotheses about climate. So climate is, I'll assume that everybody here believes that climate is probably changing. I'm not going to go into cause. And there are a lot of different ideas out there about how climate may change. Different global circulation models make different projections about what might happen, but there's pretty good consensus that, yeah, it's probably going to either get warmer or it's going to get hotter. And there's a little bit of debate out there about whether it's going to get warmer or whether it's going to get drier or wetter. So there's some variability, some uncertainty with respect to where is our reality going in the future. It's just the nature of the beast. So our question is oriented more towards how does the management interact with those boxes. So we're still kind of formulating ideas about what might happen. You know, trees are going to grow, fires might happen, owls may or may not do so well. And that may vary across our different managements and across the different climate scenarios. So our primary goal is not necessarily to say, these are our hypotheses, which I'm showing you. This is just, our project goal is really to define this space and ask the question of, so what can we do to improve the probability that we will like what comes in the future? So our overarching structure today is basically three general parts. I'll talk a little bit about starting conditions, a little bit about state and transition modeling, and a quick thank you to Lisa earlier for filling in some of those details so I can go through that a little more quickly. And then I'll pass the baton on to Jess for some of the climate impacts modeling. So to start off with the Integrated Landscape Assessment Project, we stratify our landscape at the get-go. So this harkens back to what Anne was talking about this morning. She talked about analysis unit. Well, what I'm getting to is these are our analysis units. This is how we construct them. Step one is to develop a potential vegetation type map. And this particular one was an aggregation of the Plant Association Group's map, which we got from the Forest Service down here. As you can see, there's a variety of different potential vegetation types. A little more on those later. We'll set them aside for now and look at the next map. That PVT map is intersected with what we call our ownership allocation layer, which is a layer describing who owns what across the landscape and what we think they're going to do with it with respect to management intensity. It is somewhat simplified, but at this scale, some simplification was needed in order to make it tractable. So the color coding on here is blue for BLM, green for Forest Service, pink for private, and the dark to light contrast has to do with management intensity. So the reserves are light colored and the more bright colors tend to be the general forests. And our third layer, which we intersected to get to our modeling strata, or our analysis unit, if you'd like to call it that, is essentially a fifth field HUC. So when you put all those together, you wind up with something which looks like that. I'm kind of glad I actually didn't give this talk right after lunch. I apologize. It's not very pretty. But what this shows you is that the process which we're using is not fine-grained. What we can tell after we've run our simulations is that within, say, one of those blobs, say the purple blob in the lower right-hand corner of that map, we can say this is what our model says for this patch of land as a whole, but we can't necessarily say what that patch of land looks like, how things are configured within that patch. So another way to put that, to use an analogy since it's a little late in the day, it's kind of like an art project. We're not so much like a Dutch master like this. We're not going to show you the water droplets on the pomegranate in the middle of the vegetation. We're a little bit more like a Monet. We get the overall picture, but not necessarily the precise local details. And we think this is probably good enough. We tend to avoid the surrealism. So that's kind of where we are. So keep that perspective. We're not trying to provide in my backyard predictions. We're trying to provide an overall picture. We want to say, yes, there are water lilies across a large portion of the landscape. That's kind of the level at which we're analyzing. So the next layer of information which we need for starters is, of course, what the current vegetation is out there. And we are using the gradient nearest neighbor map, which is essentially a spatial depiction of the FIA plots. And there are additional supplemental plots which come into that, which Janet Ullman, who made the maps, could tell you a little bit more about the variety of data sources which are informing this layer. It's essentially an imputation which is structured by an ordination model. I'll spare you the gory details on how it's made. Just suffice to say, it's a very useful layer that provides a statistically valid estimate of current vegetation across broad landscapes. And to some extent, the water lilies analogy works for the GNN model, as for the GNN maps as well. It's really quite robust for providing broad-scale pictures of structure and composition at a landscape scale. Although if you check it out with the in my backyard analysis, it's probably not going to hold up as well as we might like. So again, useful layer, not quite perfect. So state and transition modeling. This is the approach which we've adopted. This is kind of the way we view the world in our paradigm. And I've given you a simplified version just because the circuit board version, which Lisa showed you earlier, is a little hard to digest sometimes when you first see them. So this is simplified. We conceive of the world in boxes and arrows. And right here are the boxes which I'm showing you are just early successional forest, young forest, mature forest, and old growth forest. And there are a bunch of arrows hitching those boxes together, which represent things like growth, fire, regeneration, harvest. These models essentially work through time by allowing those arrows, the transition rates, to carry stands or pixels or whatever you want to model with, your modeling unit, through those states through time. So the pixels might bounce around for a while, and then at the end of your simulation, however many years it was, you'd be able to say, oh, look at this. Our models is saying that there's a lot of old growth forest at the end of this run. Great. So the 4-box model is a bit oversimplified, but the models which we're using for ILAP are quite a bit more complex. And this is a good thing because they carry a lot more information in them. For example, here's a box which is described as basically a grass 4 box. So this is an open vegetation state with really no trees within a dry Douglas fir forest type. Here's a box which is pole stage, single story, post disturbance. Here's a box which contains giant trees, moderate canopy closure. It's a multi-layered structure. So with that level of information, we can start to say, owls might like that box. And that allows us to get to things like habitat. I should emphasize here that there are no actual owls in our models. We don't estimate populations. We don't estimate individuals. We estimate simply area of habitat. So again, it's simplified. It's broad brush, but useful at a broad scale. Another thing we can attach to these boxes is crown fire potential. So some of these boxes are more prone to burning than others. So this is kind of how we get to the interesting attributes. Not that the vegetation isn't interesting in and of itself, but this is how we add more onto our model output. So the potential vegetation type map, by coming back to our stratification, this is what tells us which model to use where. So here's an intermediate white fir model, which gets applied to that orange stuff. The dry Douglas fir model gets applied to those bright green places. And an Oregon white oak model gets applied to that rosy area in the middle, kind of around Medford. So here's where I actually need to point out our first major problem. Within our framework, the very basic framework, which was the easiest way to get at a projection, we assume that this map does not change. So potential vegetation types are generally modeled assuming that vegetation will behave in a consistent fashion within a particular ecological zone, which is partially defined by climate. Well, when climate shifts, potential vegetation is probably also going to shift. And again, I'm happy to be able to pass the baton on to Jess because she's going to tell you a little bit more about how we help those vegetation pieces shift in just a moment. So state and transition modeling, I'm going to jump back to my STM slide again. I haven't talked very much about the transitions yet. So the dynamics of how fast the pixels move from one box to another basically has to do with what probabilities we assign to those arrows. So regeneration harvest, with the original ILAP project, we struggled a little trying to estimate what rates we should apply for regeneration harvest across all of our different modeling strata, those analysis units. It was hard to get down at information which was that fine-grained. What we're doing now is actually trying to estimate those rates based on data sources. So in this case, we pulled data from the Landsat record. So thanks to Robert Kennedy's land trender layers, we're able to finally get an estimate of what harvest rates are going on the different land ownership allocation combinations and PVT combinations. So we're finally starting to work on refining that current management scenario based on past history. And we use that same approach to estimate our fire regimes. So this is a fire history which is extracted from the Monitoring Trends and Burn Severity data set. And I'm showing some of the fires which have happened across Southwest Oregon. So this is kind of the shape of the fire regime through recent history. And this is actually something which I think, I was talking with Jane over the break, and she was talking about how the fire probabilities which we had in our models didn't necessarily work for her. Well, this is why. Our models are tuned to represent recent history. She wanted to tune some of her models to represent more of a long-term history. Well, current conditions, 1984 to 2007, fire suppression has obviously influenced these rates which we're representing. And this is actually another problem with respect to climate change. So our fire regimes are set to resemble the recent past, and this is probably something that's going to change. We need some way to tune those probabilities to allow us to go a little further forward into the future. So that said, these caveats, they come into play, they ramp up. The further off we go, the more uncertainty there is around what the climate is going to do, the more likely it is that these problems are going to shoot us in the foot with respect to our modeling and move us over into the realm of being merely wrong as opposed to being wrong but useful. So we're trying to stay within the useful realm. And in the near term, actually, it may not be such a big deal because climate may not have shifted very much. The forests won't have had very much time to respond, but as we go further out, that becomes more of a problem. So here's some preliminary results, preliminary near-term results in southwestern Oregon for that CMH project. So this is our best estimate of current management. These are a proportion of our modeling strata that have large and giant trees. So in the next 10 years, we expect things mostly to stay, go up or down a little, but not do too much. And through time, 20-year change, maybe a couple of red areas, a little bit of blue creeping in. 30-year change, few areas highlighting 40-year change. 50-year change, we're starting to see some real changes. Well, I'm starting to worry a little bit about what climate change may be doing, so it really is time for me to pass the baton on to my co-author, my co-talker, Jess.
So, thanks, Emily. All right. So yes, what about climate change? We know that a lot of physical and biological processes are either indirectly or directly tied to climate, and so they're likely to change in the future with changing climate. And as Emily said, up until the ILAP project, these state and transition models assumed a static site potential. So once a site was classified into, say, a moist mixed conifer type, it did not change over time. It stayed in that. It couldn't change to dry mixed conifer. And also, disturbance probability stayed the same through time. And so we needed a way to incorporate potential climate change effects into these state and transition models, and we used dynamic global vegetation models. These are considered to be some of the most advanced tools to assess the potential effects of climate change on ecosystems, structure and function. They incorporate information from a number of biological and physical processes, and it is a process-based model. And these dynamic global vegetation models incorporate information from global climate models to simulate vegetation structure and composition through time. The MC1 DGVM is one that was developed here at the Forest Service and Oregon State by Ron Nielsen and others. It incorporates 3 modules, submodules, one being a biogeography module that looks at the distribution of vegetation across landscapes, a biogeochemistry model that looks at the growth and mortality of vegetation through time as a function of climate, both above ground and below ground. And it also has a fire module, which simulates fire as a function of vegetation type and also the biomass from the biogeochemistry module. So MC1 doesn't incorporate the effects of management, but again, we do have this output that tells us about how vegetation types may be shifting and how fire may be shifting in response to climate change. So what we did was summarize those trends in vegetation and fire and use those to inform vegetation type changes, and fire probability in our state and transition models. So before, with the state and transition models, if a site was in, say, this xeric ponderosa pine, it would stay there. It wouldn't change over time. But what we did was link the different models together to allow shifts in vegetation type to occur with changing climate. And then we also use the MC1 output to inform our fire probability. So we could ramp up fire under different climate scenarios over time in the state and transition models. So we did this for the ILAP project in a central Oregon study area. This is about a 2.5 million acre area it's just on the east side of the Cascade Crest. Also incorporates some arid land types on the eastern portion of the study area. And these show some of the historical vegetation as simulated by, or as our potential vegetation maps for the state and transition models showed, and then as simulated by MC1. You can see the types under MC1 are much more coarse, almost more like a biome level. But historically, according to our PBT maps, the area was dominated by dry ponderosa pine, with some dry and wet mixed conifer going up into higher elevations, and also some subalpine types at the highest elevations. And then again, we have these more arid lands types to the eastern edge. Whereas MC1 showing the majority of area as a temperate needle-leaf forest, which basically encompass the ponderosa pine and dry mixed conifer types. So what we did was we basically crosswalked the MC1 types with our state and transition models. We used one state and transition model to represent each of the MC1 functional types. And then we ran MC1 under some different climate scenarios. We used 3 different global climate models, the CSIRO, MIROC, and Hadley models. Under the A2 emission scenario, it's relatively high CO2 emissions. These show temperature in the top row and precipitation in the bottom. It's the 2070 to 2099 period compared to historical, so the difference between those. And you can kind of think of these as sort of hypotheses about the future. There are over 20 different global climate models that are considered good. There's no single best model. All have their strengths and weaknesses. These 3 models in particular were chosen to kind of bracket the range of potential futures in the Pacific Northwest. So they range from relatively cool and wet to a more extreme hot and dry scenario under Hadley. Now this shows some output for the 3 climate scenarios for the study area just from MC1. You probably can't get at all the details here. They're a little bit overwhelming. But one thing to notice is that under MC1, you see these relatively fast changes, and you see, for example, these big drop-offs mid-century in the temperate evergreen needle-leaf forest. And this is because MC1 doesn't incorporate the sort of landscape legacy. It just says if environmental conditions change, then the potential vegetation changes. It can happen, it can go back and forth between years. But what MC1 did show was that it does project the continued dominance of this temperate needle-leaf forest, which is the ponderosa pine and dry mixed conifer in the study area. And then under some more extreme hot and dry scenarios, you get the appearance of new types like warm season grasslands. I won't go into too much detail on this output. But I did just want to show that the output that came from MC1 for fire. Now this does not incorporate the effects of fire suppression, but what you can get out of this is that the MC1 model is projecting a significant increase in fire under all 3 scenarios. This is separated by the forests and the arid land types. But you can see, particularly under the Hadley, a pretty dramatic increase in forest fire by the end of the century. But really, some pretty dramatic increases under all three. Excuse me. So these are the results we got when we incorporated the trends from MC1 into the state and transition models. And we put some constraints on when change could happen in these models. We basically said that we think that vegetation or that disturbance is going to be the major catalyst for change with climate change. And that these changes in vegetation type are most likely to happen in early successional conditions after a stand replacing disturbance. And so by putting those constraints on when these type changes occurs, you can see that we don't have the dramatic fluctuations that we saw with MC1. But again, we see that under all models, really, with some potential drops in mid-century, we do see the continued dominance of the dry pine and dry mixed conifer types, or some functionally similar type. Again, the appearance potentially of warm season grasslands under the hot and dry Hadley scenario. We see a drop in the amount of cool needleleaf and cold type forests, so the moist mixed conifer and subalpine types. And a potential increase in some of the types like the temperate needleleaf woodland here in this brown line here under Hadley. So that's just what the potential vegetation trends are for the study area, but what happens when you add management to that mix. So we ran two management scenarios. One we called a fire suppression only scenario that's basically no active management except for fire suppression. And we assumed that fire frequencies would be the same as they were over the past 25 years. And we used the MTBS record that Emily just talked about. And then we also ran what we called a resilience scenario, which was characterized by really light to moderate levels of thinning and prescribed burning, focused on the dry pine and dry mixed conifer forest types. And so this is the type of output we can look at. I should mention that we combined all three climate scenarios into these graphs. So these black lines are showing the mean, and then you can see some of the variation. We have the min to max range here in green. And again, results for the fire suppression only and the resilience scenario. Here we're looking at just dry forest types and their abundance, the number of hectares, over the about 90-year simulation here. You can see there's not a lot of difference in the total area of dry forest between the fire suppression only and the resilience scenario, although you do see that the minimum is potentially lower under the fire suppression only scenario. But we can look at not only just that type, but the structure within that type. And so this shows specifically the effects of management on dry forests with large trees greater than 20 inches in diameter and open canopy, so a 10 to 40% canopy cover under the fire suppression only and then under the resilience scenario. And here you can see a fairly substantial difference that under the fire suppression only scenario, this type of structure declines over time, whereas it actually increases over time under the resilience scenario. So here management did make a pretty big difference. But we also saw some interesting trends in the dry forest structure over time. And you can see under both scenarios, we see a drop in these larger size class categories and an increase in these lower size class categories. And with these models, we're seeing a substantial increase in fire and a substantial increase in the area of early successional habitat. And this suggests that it might be an issue that recruiting these large trees for these large forest structures might be an issue with increasing fire in these landscapes. So overall, we thought that our linked model suggested that there might be more vegetation resilience under climate change than this DGVM alone might suggest. In the study area, the model did suggest a continued dominance of the currently dominant dry pine and dry mixed conifer forests. We did show that in some cases that management can dampen the amount of change we see with climate change. We did run a relatively moderate restoration scenario, so it's possible that ramping up the amount of land area treated would have a greater effect. And under the current CMH project, we are working with the Olympic National Forest and coastal Washington. We're actually going to take more of a gaming approach, and they want to answer the question, well, how much do we need to treat to really make a difference, where we see this substantial increase in resilience across the landscape. So that'll be really interesting to see how that turns out. But again, we wanted to say, all models are wrong. This is potentially useful. Is this providing exact prediction of what's going to happen across these landscapes with climate change? Absolutely not. But this is a potential tool to put in a toolbox that can help get at some potential futures for vegetation with climate change. And potentially help in developing some no regrets adaptation options. Again, these models provide big picture projections, not necessarily appropriate not at all appropriate at the pixel or even project level scale, although it can give you an idea of some general trends. And unfortunately, this process is rather data, labor, and software intensive. So I wouldn't say easily replicable, but we have done a lot to streamline the process, and we're getting faster and doing it for a lower cost at this point. So I'll turn it back over to Emily for some final thoughts.
Thanks, Jess. Okay, so this was supposed to be a talk on landscape planning in the context of climate change. We've been talking a little bit more about modeling. So I wanted to take just a moment to step back and think about landscape planning, because Jess and I were in the working with the Institute for Natural Resources in the universities. We're not making decisions. Many of you are going to be making decisions with respect to formulating plans within the Forest Service and people who have power to manage landscapes, and these are conversations which are going to happen amongst lots of different people, not just people in this room, people who are, maybe listening in on the web right now, or maybe sitting at home stewing and grumbling about the way the national forests are currently managed and wanting to see something better. So this is going to be a lot of stakeholders, decision makers. They need to get a handle, presumably, on what's out there. So this is the context in which we hope that people will start to see our results. So our models here are really, they're not necessarily going to tell us this is what you need to do, but they're storytelling tools, sort of educational tools. They enable the asking of questions at really, really broad scales that we couldn't get at before, which I think is kind of cool. And in doing so, they provide realistic and plausible stories about what might happen, what might we need to look forward to and look out for in the future. And most particularly, what we want to see is that they enhance the role of science in conversations about planning. So that kind of brings me full circle back to one of those first slides I showed. So this smart old guy said something nice about science. Half of science is asking the right questions. And my PhD advisor also said this in a very different kind of way. Emily, you really need to define your questions. Either way, the message is the same. The important part comes at the beginning. So in the context of the Central Oregon study, that a lot of time went into the design of that resilience scenario to contrast with the fire suppression only scenario. And with the Climate Management Habitat Project, we're spending a lot of time working on defining what we mean by restoration and natural resources economy scenarios. And that's a lot of what we're doing now. And that involves asking questions, well, what activities are happening? At what rates are they happening? And where should they be applied across this landscape? So if you just do the multiplication, it's like 4 activities. You multiply it out by 24 ownership allocation categories and an infinite variety in rates. You can pretty soon, you get the idea. The development of these scenarios, refining those types of questions is a very involved process. So we've been asking for help. This is one of the ways in which we hope that we will devise some stories from our scenarios that will be useful outside of our own little group. So we've basically been speaking with anybody who will listen to us and asking for their input about, well, what are the things which we need to be thinking about as we devise our scenarios? What are the questions which we need to ask, which are going to develop stories which are hopefully going to be useful to you? So ultimately, that stems into our Earth Day hope for our work, which is really just to tell informative stories that are grounded in science about how different landscape management policies and plans may lead to different futures. And we want to have relevance and, we hope, credibility beyond the science community. So with that, there are a lot of acknowledgements needed here. The iLab project itself involved a large number of people, and many of those are carrying forward to the Climate Management Habitat Project. So, thank you. I'm not sure if we've got time left for questions, but...
Is there any really burning questions from the climate change talk? Well, thank you, ladies. That was really very educational.